I'm presenting my research today, Getting Too Personalized, the importance of feature choice in online adaptive algorithms. I'm Zhao Ping, and my collaborators are Luna, Nathaniel, Irene, Joseph, and Anna from Carleton College and University of Toronto. Digital educational technologies make it easy to assign students to different versions of the technology in real time, such as the video or text hint, allowing one to experiment with different ways of supporting students and discovering what is more effective. One common way of doing this is student experiment, where each student is randomly assigned to a version of the technology. But we could potentially do better than this by changing how students are assigned to conditions based on what has been effective for previous students. For instance, a student is randomly assigned a video explanation and got the next question correct. Using a multi-arm bandit algorithm, we can use the fact that the next question is correct to update our belief about the effectiveness of video explanations. Based on this updated belief, the next student will be more likely to be assigned a video explanation than a text explanation to try to maximize the learning outcome. Adapting how students are assigned to conditions can be viewed as a multi-arm bandit problem, where the system must learn from its choices about how to assign students, as it only gets information about some version of the technology by actually assigning students to that version of the technology. By both exploring how effective each version of the technology is and exploiting what has been observed so far, the multi-arm bandit algorithm can adaptively improve student experiences. I've just described the technology as adapting to show the more effective condition more often, but there's a possibility that one version is better for some students, but another version is better for other students. For instance, consider a situation where video hints are more effective than text hints for students with lower prior knowledge, but the reverse is true for students with higher prior knowledge. We would like to show video hints to students like the one on the left, while learning to show text hints to students like the one on the right. Personalizing for students seems to enhance learning technologies, but raises a crucial problem. We don't know which characteristics matter. One potential solution is to put in everything which seems reasonable for the bandit to learn a more accurate picture. However, more complexity also requires more time for the bandit to learn and explore, so the bandit may assign less students to the optimal conditions in the process. Moreover, when we include the characteristics which does not matter, we introduce the possibility of the algorithm treating students differently and accidentally discriminating against one group. This is especially problematic for characteristics which are skewed towards some values. The minority group which holds the less common value may suffer a higher cost of exploration. Literature has really shown that multi-arm bandits can help select explanations for all students and choose appropriate problems for specific students. However, there has been limited investigation of the cost of exploration for students, or how that cost is borne by particular groups of students. Outside of education, the literature on fairness and bandits focuses on somewhat different situations, but does show the minority group may bear higher costs depending on the type of scenario. To investigate multi-arm bandit behavior for pedagogical action selection, we first ran two sets of simulations for theoretical scenarios, and another one based on a real-world dataset. We used a simulation-based approach to investigate how the true relationship between student characteristics, student outcomes, and algorithmic choice impacts algorithmic performance. Simulations allow systematic consideration of variation of the environment to get a better sense of how the different algorithms and environment affect learning outcomes. In all of the work I'll show you, we focus on simulations rather than deploying these student systems with real students. Simulations allow us to examine the distribution of outcomes rather than only see what happens in a single deployment. We'll show the distribution of outcomes in the swarm plot, where every dot indicates the result of one simulation of a classroom of 250 students. For the simulations, we use the multi-arm bandit algorithm as a computational model to learn about the rewards of each action by making choices at each time step for each student. The multi-arm bandit may also consider the features of students when choosing an action. In our educational context, the algorithmic action corresponds to pedagogical action, like the type of hint. The observed reward for the action corresponds to student outcomes, like whether the students completed their homework or finished the assignment quickly. The input features for the bandit are the student characteristics, such as the previous scores of the students in the system and what prior courses the student has taken. In other words, we aim to optimize the student outcomes of students with different characteristics by learning to assign the optimal pedagogical options. In particular, we use the Thompson sampling algorithm to learn and select the next action. The actions will lead to higher success rates for the next question, when they have a greater probability of getting chosen. Constant sampling works by maintaining a posterior distribution over each action, and samples from the distributions to choose the next action. For the observed reward of the two actions in the table, we get a posterior reward distribution on the right. To choose the next action, we sample from the two distributions to select the action and give the larger value. Action 2, which has a higher success rate and thus a greater probability for the higher values, were more likely to be chosen. For our simulations, we compare between the non-contextual and contextual version of the constant sampling policy. The contextual version considers the student features in selecting the next action, and maintaining a posterior probability over the coefficients of the Bayesian logistic regression model. For the first simulation, we investigate the impact of including student characteristics for personalization, even when the characteristics do not impact optimal action choice. We aim to systematically investigate how the performance of contextual versus non-contextual algorithms is impacted by the relationship between student characteristics and the outcomes specified in the environment. As a reminder, the contextual algorithm personalizes based on the type of student, whereas the non-contextual algorithm ignores the student characteristics. We simplify the analysis by assuming that student features are binary, meaning either 1 or 0, and follows a uniform distribution, meaning that around 50% of the students take on value 1, and another 50% value 0. Also, only the first student feature impacts the new outcomes, and based on the value of the first feature, we classify the student as group 0, 1. Moreover, we limit our pedagogical actions to 2, and the rewards for group 0 are the same across scenarios. Only the rewards of group 1 changes for comparison. We also include 0 to 9 irrelevant student features which do not impact outcomes. In the educational context, there are different cases in which students with different characteristics perform differently, but that the most effective way to teach is still the same for all students. For example, the impact of one pedagogical action might be magnified for one group, but both groups are still helped by that educational intervention. We consider a number of such cases universal optimal action in the paper, although we focus on only one for the slides. Another case is that different pedagogical action is suitable for different types of learners, and we call such cases personalized optimal action. Running simulations helps us to analyze the pros and cons of personalization and evaluate whether customizing educational technologies is worth the additional complexity when we are uncertain about which scenario is likely to happen before carrying out an actual classroom experiment. We ran a simulation with the contextual and non-contextual algorithms for the two cases in 1,000 classrooms of 250 students, with one relevant student characteristics and varying number of irrelevant student characteristics. The results are graphed in a swarm plot, and every dot represents one simulated classroom. The 4 swarms for each bandit represent 4 different number of irrelevant contextual features. For both cases, the distribution for the non-contextual bandit looks really similar across the increasing number of irrelevant contextual features, because the non-contextual bandit does not account for the student features. However, the performance for the contextual bandit degrades with an increasing number of irrelevant student features, since it takes more time to explore and learn the unimportance of these additional features. Moreover, the contextual bandit experiences a greater variability in performance, and does extremely poorly in some of the simulations. For the universal optimal action scenario, these two weaknesses of the contextual bandit cause it to underperform the non-contextual bandit significantly in assigning the optimal actions. For the personalized optimal action, the non-contextual bandit performs far worse, as it does not differentiate between the two groups of students. Hence, it is not able to assign different optimal actions for different groups of students, and end up assigning the students randomly. So while the contextual algorithm may learn a more accurate model for the relationship between student characteristics and the rewards of the action than the non-contextual algorithm for both cases, the contextual algorithm is only beneficial when the more accurate model is needed to express the optimal policy, as in the personalized optimal action scenario. Also, in all cases, including context leads to more variation across simulations, which in real educational deployment result in a greater probability of the case where the adaptation has less positive impact on students. In the first simulation, we saw that personalizing for students using the contextual bandit is only beneficial for some cases. Also, in our simulations, we presume that student characteristics are equally likely. However, in the real world, some are more common than others. So for the second simulation, we ask, how does having some student characteristics which are more common impact personalization? Why might we have some student characteristics more than others? Well, Imagine that we are trying to determine what kind of hint would be helpful. The only students who see hints are those who request them or who got the problem wrong. If one student features the homework score, we might expect those who have lower homework scores and start with struggling more be more likely to see a hint than students who have higher homework scores. How then would the contextual and non-contextual bandits perform in this case? For analysis, we calculated the proportion of optimal action for the majority and minority groups. In addition, we also measured the common benchmark of fairness, the balanced success rate, which is the average of the above two measures. The graphs are for the contextual bandit, and more information about how the non-contextual bandit performs could be seen in the paper. In blue, we see the majority group, while in orange, we see the minority group. Contextual bandit differentiates students based on their characteristics, and so has to learn some information separately for the minority group. For both cases, we see that students in the minority group are worse off with their experience as compared to the majority group. Moreover, the detrimental effect becomes more pronounced with a smaller proportion of minority group size. Because the contextual bandit comes across less students from the minority group, he has less data to learn which action is effective for them. Although the overall success rate will increase for the smaller proportion of the minority group, because the majority group achieve far better outcomes. Balanced success rate decreases as the size of the minority group decreases, meaning that students in the minority group are experiencing a higher cost of exploration. This is especially problematic for the universal optimal action scenario. Students with a less common characteristic experience a version of the system that systematically disadvantages them compared to the majority group. Using a non-contextual bandit, which is oblivious to student characteristics, will lead to better and fairer outcomes. On the other hand, for the personalized optimal action scenario, the non-contextual bandit would be even worse for the minority group, because it learns which action is effective for the majority group, and wrongly generalizes it for the minority group. We'd like to see whether results for theoretical scenarios would generalize the complexities of the real-world dataset. So lastly, we run the simulations on the real-world assessment dataset to see how personalizing on student characteristics will impact student assignments in the real world. The assessment dataset includes the relationship between student characteristics, educational interventions, and student outcomes for middle school students doing math. We perform simulations that sample data from the assessment dataset and focus on previous experiments where prior performance had an impact. In particular, we operationally define the two actions as either video or text hints, the student characteristics as quartile of performance in terms of percent correct for previous assessment work, and the outcomes as having completed the homework for case 1 and completed homework quickly for case 2. The distribution of data includes 320 students in total, with around one-third in the lowest quartile of prior performance versus one-tenth in the highest quartile. Just like in previous simulations, we see more lower performing students seeing the hint than higher performing ones. Also, we see differential teaching needed for both cases. For case 1, the experimental condition is optimal for quartiles 1 to 3, but the control condition is better for quartile 4. For case 2, overall the two actions offer similar rewards, so for each quartile, the rewards of each action differs. At each step of the simulation, we sample a student to get a prior performance value. We then input the characteristics of the student in the Thompson sampling algorithm to select the next action. Then we sample from a student from the subset who have the same prior performance value and experience the same action, and use the reward of that student as the observed reward. Finally, we update the bandit algorithm just like before. The sum plot shows the results of the simulation for the two cases. The blue sum represents the non-contextual bandit, the yellow sum represents the contextual bandit, and the black line for each sum denotes the average. For case 1, we observe as expected that contextual bandits massively improve the performance for the group of students in quartile 4, though the performance of quartile 1 to 3 is slightly degraded. For case 2, the contextual bandit improves student experiences for each quartile and overall. Once again, we see some of the pros and cons of using a contextual bandit to personalize the pedagogical actions for the students, including the fact that using a contextual bandit helps only the student groups who benefit from personalization, and also display a greater variability in performance. We see the big picture that multi-arm bandit algorithms have the potential to improve student experiences in educational technologies. One issue to consider when using such algorithms is whether to personalize based on student features. Personalization using contextual algorithms may even improve the experiences of students further, compared to randomly assigning students to the pedagogical action. However, with personalization, the contextual algorithm takes longer to explore the learning effective interventions which works across all groups of students, may do poorly for some groups with characteristics that don't impact learning. Hence, using contextual algorithm helps only in some cases, and when using such algorithms in real-world educational systems, we need to carefully account for each potential feature we include. Thus, future work may examine how to add student characteristics gradually to mitigate any likely costs across student groups. Thank you for your attention.